Today we're going to talk about distance versus displacement, scalar versus vector, and finally, vector addition. First, let's start with distance versus displacement. So here you are, you're on a track, and you're going for a run. As you run around the track, the distance that you traveled is how far you've gone from where you started. So when you run all the way around the track once, you've run a distance of 400 meters. But displacement is a little bit different. Displacement only depends upon where you started and where you finished. So if you only ran halfway around the track, the distance that you traveled would follow the path of the track, and your distance would be 200 meters. But your displacement is a straight line between those 2 points. It's a vector that starts where you started and ends where you end. Now, one of the things about displacement is the fact that since it's a straight line and it starts where you started and it ends where you ended, it points in a particular direction. And that's the big difference between distance and displacement. Now here we are on the same track. Let's take a look at you running around the track one more time. As you run all the way around the track, your total distance that you travel running one time around the track is 400 meters. Whereas your total displacement, if you end in the same place that you started, your total displacement is 0. Distance and displacement are our first example of the difference between a scalar quantity and a vector quantity. Distance is a scalar quantity. For example, if somebody told you to leave your driveway and drive 200 meters, that wouldn't really tell you enough information, because you would know how far to drive, but not which direction to drive in. And that's where our vector comes in. A displacement vector describes both the distance and the direction. For example, if somebody were to tell you to leave your driveway and drive 200 meters east, then you would know where to go. Another example of a scalar quantity versus a vector quantity are these cars driving on the road. If each vehicle were traveling at 20 meters per second, that gives you a little bit of information. It tells you how fast they're going. So 20 meters per second is a speed, which is a scalar quantity. If we want to turn that speed into a vector quantity, we would have to add a direction to it. For example, to describe the motion of this green truck is traveling 20 meters per second to the east, whereas this red truck is traveling 20 meters per second west. Those would both be vector quantities, velocity vectors, with both magnitude and direction. So now that we know what vectors are, we're going to learn how to add them together. In order to add two vectors together, they have to be lying along the same line, such as vectors A and B in this diagram. Vectors A and B are both headed east, which is our positive x direction. So in order to add vector A and vector B together, we simply add them together. For example, if vector A is 5 kilometers to the east, and vector B is 2 kilometers to the east, then the total displacement is simply 7 kilometers to the east. Now, unfortunately, not all of our vectors lie along the same line, so we can't simply add them together the way they are. But what we can do is we can find the components of each vector that lie along the same line and simply add the components together. Here we have a vector that's 2 kilometers long at an angle of 30 degrees north of east. Well, this vector has a component in the x direction and a component in the y direction. So what we need to do is we need to find the lengths of those two sides, ax and ay, and use those in our vector addition. To find the lengths of those sides, you simply use the sine and cosine functions. So in order to add two vectors together that don't lie along the same line, we need to get organized. And the best way to get organized is to make a chart. Here's an example. Here we have vector A, which is 5 kilometers to the east, and vector B, which is 2 kilometers, 30 degrees north of east, the vector you saw in the last slide. Since these vectors don't lie along the same line, we have to fix that. So what we can do is we can break vector B down into its x components and its y components. The x components lie along the east-west line, and the y components run north and south. To find the x component of vector B, we take the magnitude of vector B and multiply it by the cosine of the angle, and we get 1.73 kilometers. And to find the y component of vector B, we take the magnitude of vector B and multiply it by the sine of 30 degrees and get 1 kilometer. Now that we have our vector components, we want to put them in a chart. So here you'll see a chart that has a column of x's and a column of y's. So we put all of our x components in the x column, all of our y components in the y column, and then we add straight down. So here we have 5 kilometers in the x from vector A plus 1.73 kilometers from vector B equals 6.73 kilometers in the positive x direction. Now vector A, since vector A only goes east, it doesn't have a y component. The y component of vector A is just 0, which makes things nice and easy. So the y component of vector B is 1 kilometer. So the y component of our resultant vector is just 1 kilometer. So, just like before, our total displacement starts where we started and ends where we ended. And in order to find the length of that vector, that displacement vector, we use the total x component of 6.73 as the base of our triangle, the total y of 1 kilometer as the height of our triangle, and we use the Pythagorean theorem to find the length of our resultant vector. And plugging everything in, we find that length is 6.8 kilometers. Since a vector has both magnitude and direction, the only thing we have left that we need to find is the angle, or the direction of our resultant displacement vector, our total displacement. And we use the inverse tangent function in order to do this. Along with the total y component and total x component, that we found using our chart. To find that angle, this angle right here, angle theta, we simply use the inverse tangent function of our y component divided by our x component. Now this inverse tangent function is just a button on your graphing calculator. And plugging everything in, we find that the angle is 8.45 degrees. Now I know we covered a lot today, but I just want to tell you, don't worry. We're going to have plenty of time this week in class to practice all of your new skills, and I will be right there to help you.